Welcome to the Allen School Colloquium. Today's speaker is Daniel Greer from the University of Waterloo and the Institute for Quantum Computing there. Daniel did his PhD at MIT with Scott Aaronson and has done very interesting work on the capabilities and what's possible with quantum computers. He will be talking today on the complexity of near-term quantum computers. Please take it away, Daniel.
Yeah, thanks a lot, Paul. Yeah, so my name is Daniel Greer, and this talk is going to be about the complexity of near-term quantum computers, and I'll get into exactly what I mean by that in a little bit here. But I wanted to sort of start this talk by addressing why there is all this sort of excitement around quantum computing. So there have been huge investments in developing quantum technologies from large companies, countries around the world, and even sort of a whole host of quantum computing startups. And a lot of this investment is driven by a promise that quantum computers are going to be exponentially better for certain problems. So for instance, quantum computers are known to be able to simulate complex physical systems dominated by quantum mechanical phenomenon. So for example, there's hope that using quantum computers will lead to breakthroughs in fields such as chemistry and material science. Quantum computers are also able to efficiently factor large integer numbers, a task which we believe to be hard for classical computers. And in fact, sort of the security of much of today's online communication is predicated on this classical intractability of factoring. And finally, quantum computers can help solve large systems linear equations, which could lead to advancements in machine learning. Unfortunately, all these tasks share sort of a similar problem, which is that sort of the most interesting questions we might hope to answer in each domain cannot be solved by the quantum computers that we have today. So that is, quantum computers are still a nascent technology. So to give you some sort of rough idea and maybe some perspective, on the left here is a photo of a state-of-the-art quantum computer. This is coming out of the Google group. And on the right is one of sort of the earliest electronic classical computers. As you can see from these pictures, both of these like sort of large, unwieldy machines taking up entire rooms, and yet sort of they both suffer from several limitations in their computational abilities. So what exactly are these limitations of these near-term quantum computers that I'm referring to? So sort of to start, I want to describe here what will be sort of my working abstraction for a quantum computer throughout most of this talk. So what I have shown here is a quantum circuit, which has sort of the same general components that you'll know from classical circuits. So it has input states, which are known as qubits. It has gates, which are sort of quantum operations acting on small numbers of qubits. And it has measurements, sort of a randomized process that produces a classical bit string from the output of the quantum circuit. And sort of the feature of near-term quantum computers that I want to highlight is noise. So at any stage of the circuit, the operation you are attempting to apply has some error. And these errors add up. So if you have too many operations, the error in the output will swamp any signal that you were trying to measure in the first place. So the implication here is that for quantum computers of the near term, sort of we are restricted in the number of operations that we can apply. We can sort of either have few qubits or few gates. And some of you may have heard this term NISQ, referring to sort of noisy intermediate scale quantum computers. And this is sort of exactly the type of restricted quantum computer that I'm referencing here. Sort of using the phrase near term to refer to this sort of NISQ era, but they're essentially the same thing, and they should sort of connote different things. I will try to avoid making sort of concrete predictions about exactly how long this NISQ era is going to last, but sort of today's quantum computers are quite far from being able to implement error correction on a large scale, which is what is needed to avoid the limitations that I've described on this slide. So in light of this, let's look at some examples of quantum computers that we have today. So on the left is a processor for IBM's Falcon quantum computer, which has 27 qubits and can compute circuits at depth about 12. And on the right is Google's Sycamore quantum computer, which has 53 qubits and a depth about 20. So you can sort of see from these statistics that these are relatively small numbers of both qubits in depth. But I also want to sort of mention another limitation of these sort of near-term quantum devices, which is going to come up again later in this talk. And that is, for each processor, the qubits have to sort of be physically arranged in sort of a 2D geometry described by a graph. So we sort of zoom into this graph, we have that each gray dot here represents a qubit and the location of a qubit. And each blue line indicates where the gates can be applied. That is, the gates can only be applied between qubits that are neighbors in this graph. And this is a property called geometric locality. So from these diagrams, you can see that, we already have a quantum circuit whose depth is quite small. And so if we constrain sort of the locality of the gates as well, we are sort of restricting what the quantum circuit can do even more. This sort of leads to a natural question, and sort of maybe the central question of this talk, which is, what can we do with these near-term quantum computers? And sort of more specifically, are they already better than classical computers? So there have been sort of several proposals from what you might be able to do with a near-term quantum computer, ranging from chemistry to combinatorial optimization to machine learning. But, you can ask the question, do these proposals actually outperform, what you could do with a classical computer? And, this is unknown. So sort of unfortunately, in each case, the sort of purported advantages are only heuristic. And many of the results attained with, near-term quantum computers can be efficiently replicated with a classical computer. So this motivates sort of the central theme of this talk, which is quantum advantage. That is, proving near-term quantum computers can solve problems that cannot be solved by classical computers. Notice that this is sort of both an experimental challenge, since we need to be able to solve some problem in a real-world quantum experiment, and a theoretical one, since we need to prove that classical computers cannot sort of easily replicate the behavior of the quantum device. And my research is on sort of the theoretical aspects, proving rigorous theorems about the classical intractability of quantum computing experiments. But before I tell you sort of about my specific results, let me try to explain some of the challenges in this area. So first, theoreticians working on classical algorithms are constantly making progress. So candidates for quantum advantage that sort of once looked promising sort of were eventually refuted by improvements to the classical algorithms for those problems. And in some sense, the examples I showed on this slide are a bit unfair, because these were quantum algorithms that were designed for specific applications in machine learning and optimization. However, even quantum experiments that were explicitly designed to dodge classical simulation methods have had to contend with sort of increasingly sophisticated classical algorithms. So for example, let's look at Google's famous 2019 Google quantum advantage experiment, where they performed some task on a quantum computer in 200 seconds that they claimed would take 10,000 years to simulate on a state-of-the-art classical supercomputer. However, soon after Google's paper was published, a team from IBM blogged about a different method of classical simulation, which they estimated would only take about 2.5 days. And soon enough, sort of teams across the world started implementing and sort of refining these ideas to the point where we now have a classical simulation algorithm running in only 304 seconds. Sort of a far cry from this original 10,000-year figure. And you might look at this and say this is somewhat discouraging. You could also counter that from a sort of a complexity theoretic perspective. The difference between 304 seconds and 10,000 years is just, in some sense, it's just a constant. And as you increase the size of the quantum experiment, the classical simulation task sort of becomes exponentially more challenging. And so, eventually, these classical simulators they won't be able to keep up, and they will fail. Unfortunately, it turns out that even though this is sort of a nice complexity theoretic perspective, even proving rigorous quantum advantage in this regime is challenging. So why is this so challenging? So to see why these provable separations are difficult, let's first consider sort of the complexity class P, which captures all the problems that we can efficiently solve on a classical computer. Containing the class P is the complexity class BQP, which captures all of the problems that you can efficiently solve on a quantum computer. So for example, we know that quantum computers are at least as powerful as classical computers. And then containing BQP is the complexity class P space, which captures all of the problems that you could solve on a classical computer using a small amount of memory, though perhaps a large amount of time. So in summary, what we've shown here is that P is contained in BQP, which is contained in P space. But now suppose that you could rigorously prove quantum advantage. That is, you could show that quantum computers could solve problems that classical computers cannot solve. So this would imply that P is not equal to BQP. And by transitivity, this would imply that P is not equal to P space. But as many of you will know, sort of the P versus P space problem is sort of one of the major unanswered questions in theoretical computer science, sort of commensurate in difficulty to some of the other famous complexity theory questions like the P versus NP question. So how then can we hope to prove quantum advantage in the face of these complexity theoretic obstructions? So let me give you sort of two main ideas, both of which I'll sort of tackle in this talk. So the first idea is that we can sort of relax what we mean by quantum advantage. In particular, we can restrict the set of classical algorithms that can be used to simulate the quantum experiment. And this is actually more fair than it might sound at first, because given that near-term quantum computers are restricted in several ways, it makes sense to compare them against classical algorithms that have similar restrictions. And the first result I will tell you about falls into exactly this category. I will show that constant depth quantum circuits can solve problems that constant depth classical circuits are unable to solve. In fact, in the follow-up result, I will show a classical simulation strategy for these circuits, which in some sense pinpoints the exact features of this quantum experiment that make it hard to simulate. And finally, there's a second idea to contend with the complexity theoretic obstructions we saw in the previous slide. That is, accept that you're going to need some conjecture to prove quantum advantage, but now just try to use the best, least speculative conjectures that you can. And in the final result of this talk, I also do exactly this. I will improve the theoretical evidence for quantum advantage using what are known as linear optical quantum computers. And I'll do this by sort of eliminating the reliance on a conjecture that was previously required. So let me start by talking about how to obtain unconditional quantum advantage using constant depth quantum circuits. So let's start by sort of revisiting our picture of a quantum circuit. And recall that the key feature of near-term quantum computers is that they have low depth, where once again, this depth is defined as the number of layers of gates required to implement the circuit. So for example, the circuit depicted on this slide has depth 4 because it has these 4 layers of gates. But let's also consider a model of near-term quantum computers where the depth is restricted to constant. That is, as we consider larger and larger circuits, the depth remains the same. So we can have as many qubits as we like, but the depth has to be constant. This is a restricted model of quantum computation, sort of mirroring what we need with near-term quantum computers. And we can now ask the question, are constant depth quantum circuits more powerful than constant depth classical circuits? And sort of remarkably, the answer is yes. So the first result of this kind was proved by Bravey, Gassett, and Koenig, who showed that constant depth quantum circuits cannot be simulated by bounded Fanon constant depth classical circuits consisting of and/or NOT gates. So sort of pictorially, we get the separation shown here with the classical circuit on the left and the quantum circuit on the right. And the thing to notice is that these two circuits are restricted in the same way. So both have constant depth and both have bounded Fanon gates. That is, their gates only act on a constant number of bits or qubits. And yet, the quantum circuit is still solving problems that the classical circuit cannot solve. So in the language of complexity theory, there's a separation between the complexity class NC0 and the quantum complexity class QNC0. And it's worth emphasizing that this result is unconditional, does not rely on any conjectures to prove its results. And while this is a fair comparison between circuit classes, and you could say, well, maybe this is the end of the story. We could hope for more. That is, we could ask, are there even larger classes of classical circuits that are unable to simulate these simple constant depth quantum circuits? And once again, the answer turns out to be yes. So follow-up work by Beniwatz, Kothari, Schaefer, and Tal showed that even when the classical circuit is allowed to have unbounded Fanon gates, that is, and OR gates that can act on arbitrarily many inputs, these classical circuits still cannot simulate the constant depth quantum circuits we saw on the previous slide. And it's natural to ask how long we can continue to prove separations like this. Can we keep adding power to the classical circuits without giving them the ability to simulate these quantum circuits?
So Daniel, so question came in from, so are you requiring the same depth on both sides, or can one be different from the other?
As long as they're both constant depth, that's fine. The QNC0 circuit, the quantum circuit, will have a fixed depth of 4. And as long as the classical circuit class also has some constant depth, it could be an arbitrarily high constant, then it still cannot simulate the circuit.
Thanks.
Thanks for the question. So the answer is, can we go further? And it turns out that you can. So the result of mine that I want to tell you about is that we can continue to prove these separations. In fact, these separations can be quite dramatic. So first, let me describe to you what we can prove unconditionally. So we prove that even when you add a parity gate to the classical circuit class, these classical circuits still cannot simulate these constant depth quantum circuits. And this result is what is in some sense the largest known unconditional separation between natural classes of quantum and classical computers. But let me sort of now also try to explain to you another reason why the addition of these parity gates is significant from sort of a complexity theoretic historical perspective. So stepping back for a moment, let's look at sort of the sequence of separations that were shown. We started with a task that could be solved by a constant depth quantum circuit that could not be solved by any classical circuit in the class NC0. Then we increased the power of this circuit class to AC0. It has unbounded Fanon gates. And even these circuits still could not simulate the quantum circuit. And finally, with our result, we increased the power of the class yet again to AC02 by adding parity gates. And once again, these circuits still cannot simulate the quantum circuit. And sort of importantly, for each one of these steps, we knew that we were sort of strictly increasing the power of the classical circuit due to famous results in complexity theory. But unfortunately, this is sort of right at the limit of where unconditional separations in complexity theory are known. And it turns out that if we had better unconditional separations in classical complexity, this would lead to better unconditional separations between quantum and classical circuit classes. So for example, if we could show that NC1 is not equal to L, then we could show a quite dramatic separation between quantum and classical circuits. That is, not even log depth classical circuits could simulate these simple constant depth quantum circuits. So now that you have some context for this result, how do we go about proving it? I want to start by describing the task that was used for the first 2 separation results I showed you. And this task will not be the task that we use for our result, but it shares some similar characteristics, which will be important. So for each input length n, we'll have some fixed constant depth quantum circuit on n qubits that is shown here on the slide. And specifically, this input is going to be a list of single qubit gates. And the problem for the quantum circuit is to simply apply those gates, measure the resulting quantum state, and return the measurement outcomes as an answer to the problem. The task is defined in such a way that sort of any valid measurement result is sufficient. And so a classical simulator accomplishes this task if it can return any of the results that the quantum circuit might have responded with. This simple task, which by design can be solved by a constant depth quantum circuit, cannot be simulated by either NC0 or AC0 circuits due to the prior work in this area. Unfortunately, to get stronger results, to get the results that we obtained, we found that this task was no longer sufficient. And in fact, we conjecture sort of a specific separation in complexity theory that helps to explain why some of these new ideas are needed. Though this argument is somewhat subtle, so I'm not going to try to explain exactly how this works. But what is this new ingredient? So the new ingredient that helps us prove our result is interactivity. So that is, the input to the quantum circuit is given in multiple rounds. So in the first round, the input is once again a set of single qubit gates. But for now, only for some of the qubits. And once again, the quantum circuit just applies those gates, measures the corresponding qubits, and returns the measurement outcomes. And then in the second round, the input is a set of single qubit gates for the remaining qubits. And the quantum circuit performs the same process of measuring those qubits and returning the results. And once again, we say that a classical simulator passes the test if it can produce any valid transcript of the interaction that the quantum circuit might have produced. So why are we switching to interactive tasks? It may seem as though this interactive task is sort of exactly the same as the non-interactive task I described before. And the quantum circuit is essentially identical. However, there's actually sort of a subtle but important distinction between the two settings. And to see this, imagine that I have a classical circuit which passes this interactive task. In fact, I've drawn it as an AC02 circuit here, but in reality, we could replace this with almost any classical simulator. And let's look at what happens after the first round of interaction. The key idea is that the classical simulator must have had a classical internal state between rounds 1 and 2. What this means is that after the classical simulator returns some answer to the second round questions, we can record those answers and reset, or as it's known in cryptography, rewind the classical machine to its state immediately after the first round. This ability to rewind means that we can ask multiple questions in the second round where all of the answers must be consistent with the answer the classical simulator gave in the first round. So we can probe the classical simulator on different sets of second round gates, and we will be able to extract a lot of information from this interaction. So now we have this sort of powerful primitive of rewinding. So let me present sort of a high-level proof for why these weak circuit classes cannot simulate this interactive task. So let's start by looking at this interactive task from the perspective of the quantum circuit. In the first round, the quantum circuit measures most, but not all, of the qubits in the circuit. And what is left over on the remaining wires is some quantum state. And using a technique called measurement-based quantum computation, we can show that if you knew exactly what the state was, then you could solve some hard problem. So technically a problem in the complexity class PARE-DL. But let me now argue that if you did have a classical simulator for this task, then you could determine what this state was, and therefore you would be solving this PARE-DL hard problem. So first, we'll use the idea of rewinding to make many measurements of this state. And then using a principle called quantum contextuality, we can sort of process those measurement results together in constant depth to determine what the underlying state actually was. And we sort of combining these two facts together, we sort of arrive at the sort of following theorem or conclusion. So if you had a weak classical simulator for this interactive task, so for example, an AC02 circuit, then you can use it to solve problems that you sort of shouldn't be able to. So technically these PARE-DL hard problems. And since this is a contradiction, this implies that there are no weak classical simulators of this type that can pass the interactive task. So I sort of wanted to end the sort of technical portion of this section by pointing out that one of the nice things about this result is that we had to sort of combine results from several different fields using sort of a large variety of techniques. So in order to prove this separation sort of rigorously, we needed ideas from cryptography, such as rewinding and Killian randomization. We needed ideas from classical complexity, such as the theory of branching programs and separations in classical circuit complexity. And we needed fundamental results from quantum information and computation, such as measurement-based quantum computation and quantum contextuality. And I like this slide because I think it exemplifies that proving quantum advantage is sort of, it's a very challenging problem. And to move forward, I think it's going to require sort of the collaboration of a lot of different fields.
Thanks. Daniel, can questions come in? Does this argument that you described before, does it work also for a randomized circuit simulator or only against deterministic circuit simulators?
It works against randomized as well. Yeah, you can do sort of the standard thing where if you had a randomized circuit, you just fix the best setting of the random bits, and then you sort of reducing back down to a deterministic circuit. But yeah, it works for randomized circuits.
Thanks.
So yeah, so to summarize this section, I showed that constant depth quantum circuits can solve problems that constant depth classical circuits cannot solve. So this was the largest known unconditional separation between the power of quantum circuit and classical circuits. And furthermore, we show how to lift separations of classical complexity classes to obtain even stronger separations between quantum and classical computers. And recall, the whole motivation for this section was that constant depth quantum computers have these errors. And you could ask the question, what if we explicitly added this error into our circuit model? And in follow-up work, what we show is that these separations still hold even when you have these errors. So there's some interactive protocol that a noisy constant depth quantum computer can complete that no AC02 circuit could simulate. So I think this is a natural point to stop for questions, Paul, if there are any.
So I have a question. So these circuits, I mean, in general, the classical circuit could have arbitrary connection between them. What about the quantum circuits?
Yeah, thanks for setting up the next part of my talk. Yeah, so the quantum circuits actually have they lie in a very nice, simple geometry, and that's exactly sort of what I want to talk about in the next part of my talk. So maybe I'll just get to that. I sort of want to talk about sort of the other side of quantum advantage, which is, when do you have efficient classical simulation algorithms for these quantum computing problems? And in particular, in this section, I'm going to look at sort of in detail what the best classical simulation methods are for the circuits that we just saw that were used for quantum advantage. And to do this, I'm going to point out sort of two extra nice sort of additional properties that I didn't mention earlier about these quantum circuits that were used for quantum advantage. And exactly as you point out, they have a nice geometric restriction. So if we look at their qubit layout, just like we saw for the quantum processors used by IBM and Google, these quantum circuits have qubits that are located at the vertices of the graph with gates that are applied between adjacent qubits. And in fact, there's only a single gate called a CZ or a C sign gate that is applied per edge of this graph. So only one gate per edge. And this CZ gate is an example of what is known as a Clifford gate. In fact, all of the gates in the constant depth quantum circuit used for quantum advantage are examples of Clifford gates. And Clifford gates are somewhat remarkable because they actually appear in sort of a large variety of quantum computing contexts, but they're a non-universal set of quantum gates, and they can be simulated in polynomial time. And in particular, sort of a famous result in quantum computation called the Gottesman-Canil theorem states that any constant depth quantum circuit constructed only of Clifford gates can be simulated in polynomial time, or sort of more precisely n cubed time, where n is the number of qubits in the circuit. So, recall that the quantum advantage result I described in the previous section was, in large part, a statement about the depth of the circuit. We showed that constant depth Clifford circuits cannot be simulated by constant depth classical circuits. But on the other hand, the Gottesman-Canil theorem states that these constant depth Clifford circuits can be simulated efficiently by classical algorithms that have no depth restriction. And at first, this may seem to be showing us a complete picture, identifying depth as sort of the key feature, which is leading to sort of this quantum advantage. But if we look more closely at the difference between quantum circuits and classical algorithms, we see something else kind of interesting. So the quantum circuit was implemented on the edges of a 2D grid graph. And sort of because we apply exactly one operation per edge, the sort of total number of operations that were used for the task was about n. But on the other hand, the Gottesman-Canil theorem requires n cubed many operations. And even sort of subsequent improvements by Bravais, Gassett, and Koenig didn't suffice to sort of close this gap. So this raises sort of an interesting question, do constant depth Clifford circuits solve tasks with fewer operations than classical computers? And so for the remainder of this section, I want to describe to you, our result giving what is in some sense a negative answer to this question. we show that there exists plausible linear time classical algorithms for a large range of Clifford simulation problems defined over graphs. And this sort of the takeaway here is that this sort of helps to confirm our previous intuition that depth was indeed sort of the key feature which was leading to quantum advantage for these tasks. So what is the precise theorem? The theorem we prove is the following. There is an n to the omega over 2 time classical algorithm for simulating constant depth Clifford circuits on a 2D grid. And here, this constant omega is what's known as the matrix multiplication exponent. It's the smallest number for which two n by n matrices can be multiplied in n to the omega time. And let's just take a look at some of the range of values that omega can take. So on the far end is 3, which is just given by the fact that the standard algorithm for multiplying two n by n matrices takes n cubed time. And on the other end of the spectrum is a lower bound of 2, because it takes n squared time to simply just write out all of the elements of the product. And then over the years, algorithms for matrix multiplication have gotten sort of increasingly better. And now we know that omega falls somewhere in the regime of between 2 and 2.373. And consider for a moment that omega does actually equal 2. Then we get sort of a surprising consequence, right? Plugging 2 back into our theorem, we obtain sort of a linear time algorithm for simulating constant depth Clifford circuits on the grid, which matches sort of the number of operations that we saw with the quantum circuit. So in terms of techniques, I want to mention sort of 2 new contributions to Clifford circuit simulation that go into proving this theorem. So first is the generic use of fast matrix multiplication subroutines. That is, our theorem can often be used in sort of a black box manner to improve the theoretical efficiency of simulating Clifford circuits, such as those that appear in quantum error correction or entanglement purification, as just 2 examples. The second contribution is that we leverage the geometry of the circuit for faster simulation. And to sort of separate this contribution from the previous one, for the rest of this talk, I'm just going to sort of use naive matrix multiplication algorithm for the remainder. So when we replace omega by 3, the theorem gives an n to the 3/2 algorithm for simulating constant depth Clifford circuits on a 2D grid. And so for the rest of the section, I'm going to try to describe the intuition behind this algorithm. But first, let's look at some sort of implementations of these Clifford simulation strategies, sort of in the absence of these fast matrix multiplication techniques. So in the plot on the right, I've shown how our algorithm compares to the previous state-of-the-art simulation techniques for simulating these Clifford circuits. So you can see the sort of the theoretical advantage of our algorithm translates to a practical advantage as well. At the extreme, we are able to simulate Clifford circuits consisting of like 400 million qubits on a laptop computer in about a day. And in fact, it turns out the classical simulation algorithm that I just described for Clifford circuits in 2D geometries is a special case of a more sophisticated algorithm for simulating Clifford circuits in arbitrary planar graph geometries. So in this setting, the qubits are once again located at the vertices of graph, in particular, any planar graph. And there are most constantly many gates applied between the neighboring qubits in the graph. So there's sort of an interesting distinction here between this case and the previous, which is that, in both cases, there are only a constant number of gates applied per edge. But because vertices in a planar graph can have high degree, this doesn't mean that the circuit can necessarily be implemented in constant depth because of this degree change. And what we prove is that the simulation speedup holds in this more general setting. So there's an n to the omega over 2 time classical algorithm for sampling the outputs of planar Clifford circuits. And in fact, this classical simulation strategy implies a new algorithm in classical complexity. So this is sort of a spin-off or a quantum-inspired classical algorithm, you might say, where we show that there is an n to the omega over 2 time classical algorithm for solving linear systems mod 2, where the linear constraints are given by the adjacency matrix of a planar graph. So this extends the work of Alon and Yuster, which only worked for invertible linear systems. So let me now try to give sort of a brief proof sketch of this theorem. We started with a Clifford circuit defined over a planar graph. And as it turns out, we can assume without loss of generality, using techniques from measurement-based quantum computation, that the circuit is of the usual form that we saw earlier, with a single CZ gate acting between each qubit sharing an edge in the graph. And using this construction sort of immediately gives us sort of a straightforward way of building the quantum circuit, which we could then simulate using standard techniques. Unfortunately, this approach hasn't really yet used anything specific about the planarity of the graph, and it will be too slow. So to leverage planarity, we turn to techniques from algorithmic graph theory. So first, we label every vertex, and we build what is known as a tree decomposition for this graph. And the most challenging aspect of our proof is to take this tree decomposition and build sort of a complicated circuit of our original planar Clifford circuit, except now sort of the components of this circuit mirror the structure of the tree decomposition. And sort of, what have we done by introducing all this complexity? Well, it turns out that because the original graph was planar, these subsystems will be relatively small. And so we can choose to simulate the circuit sort of bit by bit, merging subsystems when they meet, and introducing new subsystems only when we need them. So in this way, we can sort of eventually simulate the entire circuit with relatively small overhead. So in summary, this section focused on developing fast classical simulation algorithms for Clifford circuits in planar geometries. And it's worth emphasizing that these were exactly the types of circuits that were used for quantum advantage in the first part of this talk. And so these algorithms sort of reveal the key role that depth is playing for provable quantum advantage. We also showed how these simulation strategies lead to better classical algorithms for problems in linear algebra than were previously known. And finally, I want to mention that these simulation strategies for planar Clifford circuits have proven to be very useful in other contexts as well. So for example, in later work, we were able to extend these techniques to non-Clifford circuits in planar geometries. Obviously, we're not going to get polynomial time algorithms, but they will be sort of faster than the most naive algorithms. So for the last part of this talk, I sort of want to switch gears a bit. So if you didn't like the Clifford stuff, you can sort of tune back in. And I want to talk about quantum advantage results where we compare against the full power of classical algorithms. So, the real question here is, can near-term quantum computers solve problems that no efficient classical computer could solve? And this section is going to focus on sort of an extremely popular proposal for obtaining this type of quantum advantage called boson sampling that was introduced in 2010 by Aronson and Arkhipov. And at its core, sort of boson sampling idea is very simple. It's just that the dynamics of a random linear optical system are hard to simulate. So what is a random linear optical quantum system? Let me try to give you sort of a toy model for how these linear optical systems work. So each state of the system consists of some number of photons and a set of modes or locations where these photons can be in. And I'm going to use the words modes and photons a lot for the rest of this talk. So it's sort of worth reiterating that each one of the M modes is just a type of location that one of these N photons can be in. And so in the picture I've shown here, each of the N photons is in a distinct mode, but you can have states where multiple photons are in the same mode. And you act on these states by linear optical transformations that act on the modes of the state. So in a boson sampling experiment, we sort of shoot the photons into this linear optical system. There's some kind of quantum interference. And at the end, we sort of measure the photons and we find that they've been scrambled in some way. And the sort of theorem, the main theorem of Aronson-Arkhipov in the boson sampling paper is the following. There's no classical polynomial time algorithm to approximately sample from the output distribution of the boson sampling experiment, modulo 4 conjectures in complexity theory and random matrix theory. And for the purposes of this talk, I want to sort of only focus on this last conjecture. And in fact, sort of glossing over sort of the precise statement of the conjecture, let me sort of claim without proof that this conjecture has the following implication. This physical interpretation for our boson sampling experiment. It states that we can get classical hardness in the regime where the number of modes is quadratic in the number of photons. Or in other words, that M is roughly N squared. But you could ask the question, what if in an attempt to sort of make our hardness argument more rigorous, make this theorem require fewer conjectures, we try to just sort of eliminate this last conjecture? Well, Aronson and Arkhipov then show that we can obtain classical hardness, except now we need m to be roughly like n to the 5th power. And this is sort of unpleasant. So why is this unpleasant? Well, if we look at sort of the real world boson sampling experiments, we see that this parameter regime where you have many more modes than you have photons is unrealistic. And there are two sort of high profile experiments coming out of the USTC group in China. And in the first experiment, there were about 45 photons and 100 modes. And in the second experiment, there were about 113 photons and 144 modes. And what we can see here is that incorporating a lot of modes into your experiment is costly, which is why these experimentalists do not do it. So it begs sort of a natural question: how can we sort of maintain the theoretical hardness of our argument while moving to these more experimentally motivated parameter regimes? And the result that I want to present to you does exactly that. So we show that there's a linear optics experiment using only quadratically more modes than photons that cannot be simulated by any polynomial time classical algorithm. And it's worth emphasizing that it uses the standard boson sampling conjectures, except it does not need the last one. So we're getting hardness from the same set of relatively well-tested conjectures, but we don't require the use of the last one. And it's also worth pointing out that the inputs to this linear optical experiment are Gaussian input states rather than the single photon states I described in the first slide of the section. But this is a setting called Gaussian boson sampling. And you might be somewhat worried because I may have sort of sneakily increased the complexity of things in these sort of Gaussian input states. But actually, this is sort of the dominant form of boson sampling used today. Both of the experiments that I described earlier were these Gaussian boson sampling experiments. So let me give you some sort of idea or intuition for how we prove this result. So to do this, I first sort of need to describe the original boson sampling experiment and where the conjecture comes up that we need to eliminate. So to start, you need to know that the linear optical transformation in a boson sampling experiment is given by an m by m unitary matrix, which we'll call U. And the dynamics of the boson sampling experiment are then described by the submatrices of the unitary matrix U. So for example, suppose we want to calculate the probability of measuring n photons in each of the first n modes, then this probability is given by some function of the first n by n principal submatrix of U. And while it's not clear from what I've told you, the sort of required property that we need for the theoretical hardness argument of boson sampling is that if we're given a random unitary matrix U, then its n by n submatrices look like matrices with IID Gaussian entries. And this is sort of exactly the source of the problem that required a conjecture. We only have rigorous bounds on the rate of convergence to Gaussian when m is like n to the 5. And so how do we get around this problem? The idea is to sort of directly encode the Gaussian entries into the experiment. So we prove that there's a Gaussian boson sampling experiment which simulates the dynamics of a normal boson sampling experiment, except instead of the linear optical system being governed by a unitary matrix U, it's now governed by a matrix G, whose entries are IID Gaussian by design. So sort of revisiting the example from before, if we were trying to calculate the probability of measuring a single photon in each of the first n modes, by our construction, this probability is given by the same function f applied to the n by n principal submatrix of G. Except by design, this matrix is exactly Gaussian. And in some sense, this is sort of all we needed for the remainder of the boson sampling proof. We can sort of pick up where they left off and sort of just plug in this argument. And we would almost be done, except we introduce, as part of this process, sort of somewhat nasty looking normalization factor. And it turns out to sort of get the argument to go through and prove classical intractability, we need to prove rigorous bounds on this normalization factor. And this normalization factor depends on the singular values of G. So in some sense, you might say that we've just traded sort of one problem in random matrix theory for another, and we haven't really made any progress. Except this is a problem in random matrix theory that we are actually able to solve and bound in this regime. And so, brushing sort of a lot of details under the rug, this sort of finishes the outline of the proof. So in summary, what have we shown? We designed a linear optic experiment and proved that it cannot be efficiently simulated by any classical device modulating these conjectures. And there's sort of two ways to view this quantum advantage experiment in comparison to what was previously known. So the first way is to look at this result is to say, well, it uses the standard set of conjectures, but it holds in sort of a more experimentally friendly parameter regime. And then in the second way you could view this result is say, well, it works in sort of the standard parameter regime, but it uses strictly fewer conjectures. And finally, what some of you may be asking, and what I want to address, is what happens in the regime where the number of photons is approximately equal to the number of modes, the parameter regime, which is in some sense sort of the most experimentally motivated. In our paper, we show that classical intractability probably still holds, but to sort of prove this result, we require some non-standard conjectures. So I think there's still room for improvement there. So what is the sort of outlook and future directions of this work? So let's start by sort of revisiting the motivating question for this talk, which is, are near-term quantum computers better than classical computers? We looked at sort of two models of near-term quantum computers, both of which have enjoyed some level of experimental success, constant depth Clifford circuits and planar geometries, and random linear optical systems with Gaussian input states. And in each case, I proved a quantum advantage result, showing that these near-term quantum computers have capabilities beyond those of their classical counterparts. So in other words, I proposed specific experiments that you could run, which if successfully implemented, would demonstrate some computation that was truly quantum. And here I sort of want to make the sort of meta level point that this research sort of emphasizes a developing connection between complexity theory and experimental physics. That while physicists have been tasked with a challenging goal of building a working quantum computer, computer science and complexity theory are sort of playing increasingly important roles, guiding quantum experiments of the near term and providing rigorous mathematical evidence for classical intractability. So where is this research going? Let's first look at quantum advantage. There's really two requirements. First, we need to find some task which is easy to implement experimentally. And second, we need to prove that it's hard to simulate classically, perhaps modulo some conjectures. Unfortunately, these two requirements are often in tension. So the easier the task that we use, sort of the more speculative the conjecture we might need in order to show that it's classically intractable. And so my goal for the future is to really try to shrink this practice theory divide as much as possible, obtaining strong theoretical guarantees with experimentally easy tasks. So for example, we saw earlier in my work on Gaussian boson sampling that we can move to a more experimentally friendly parameter regime without sacrificing any of the theoretical rigor of that hardness argument. But there are other aspects of experimental setups which could be incorporated into our hardness argument. So for example, these boson sampling experiments are usually done with something called threshold detectors, which can only detect if there's at least one photon in a particular mode. But the theoretical arguments assume that you can count exactly how many photons end up in each mode. So this distinction gives rise to new dynamics, and you sort of need to carefully account for them if they're going to go into your theoretical hardness argument. And I have some current work which sort of gives some evidence that this setup is still classically intractable. Another idea that I'm very interested to pursue is using interactivity for quantum advantage. So we saw earlier in the Clifford setting that interactivity was key in giving us stronger separations against classical circuit classes. And a key question here, I think, is whether or not some of these ideas can be ported to experimental setups using non-Clifford gate sets. And if you could get this to work, there are some reasons to believe that this could sort of help to avoid some of the common pitfalls that are used in the usual setting without interaction. And finally, I also want to briefly touch upon sort of the other side of quantum advantage, which is classical simulation. Much of my past research has been on the simulation of Clifford circuits, but today's quantum computers are able to implement, non-Clifford gate sets. So, you could ask the question, how does the simulation of Clifford circuits inform quantum computation? What else are these techniques good for? So, let me give you two ideas. So first, it turns out that because Clifford circuits are officially simulable, they can be used to parameterize quantum circuits. That is, quantum circuits can be simulated in time, which is exponential in the number of non-Clifford gates in the circuit. These techniques imply that we can speed up classical simulation of general quantum circuits by finding better algorithms for Clifford simulation. So one natural question here is how we can port the matrix multiplication speedups we saw earlier to this setting. There's sort of there's a subtle reason sort of related to the calculation of global phase why this just doesn't immediately follow from the previous work that I showed you. And finally, we saw earlier that the classical simulation of planar Clifford circuits leads to faster classical algorithms for solving planar linear systems of equations over the field of 2 elements. And in ongoing work, we can actually show that these fast algorithms are quite general and can be made to work over arbitrary fields. So in general, there's just a very tight connection between the Clifford group and problems in linear algebra, and these new simulation algorithms may continue to uncover new classical algorithms for these problems. So that's all I wanted to say, and thanks a lot.
Thank you. So I'll start with a question. So you teased with the use of interactivity, and the question I was wondering. So you did 2 rounds of interaction and to get some of your results. Are there do you think more rounds are going to help, and are there tasks, natural tasks, where you think there's inherent, like a task that you'd actually be interested particularly in solving that has rounds of interaction associated with it, other than the specific get these outputs of these single qubit gates?
Yeah, it's a really interesting question. There's a sense in which if you add interaction, it's kind of cheating. So if you add too many rounds of interaction, then what you can use this technique called measurement-based quantum computation, which is we use it in our result, but we use it in like a very subtle way. There's a more straightforward way where you can take a highly entangled resource state. You can measure a particular qubit of that resource state. You'll get some response. Based on that response, you measure another qubit, and so on and so forth. And if you sort of follow the sort of principles of this technique, you can sort of affect any transformation that you want to in this way. So you can simulate general quantum circuits. So yes, if you added a lot more layers of interaction to your circuit, you could do very powerful things with these circuits. But sort of, I think our view is that that's sort of, or my view at least, is that's sort of cheating, because quantum computers of the near term have like pretty small coherence times. So like they're not going to sort of exist in memory for very long. And so like these back and forth with a classical machine is actually quite expensive. So I think if you're going to have interaction, then it needs to be restricted to like constantly many rounds for it to be sort of physically motivated. Does that make sense?
Sure, but 3 or 4 or something like that might give you something more, but some constant rounds.
Yeah. Yeah, there's some really subtle ways, problems and issues that come up in how exactly you define what an interactive problem is. One of the really nice things about the Clifford setting and our work is that you can sort of define exactly what it means to simulate the interactive protocol in sort of like the loosest possible way that you could imagine. Like you just return anything in the support of the distribution. But when you sort of move to sort of more general systems that have non-Clifford gate sets, and you introduce noise and whatever, like everything is going to be in the support. The question really becomes like, how do you pick out the states that have high amplitude, and that then it gets the questions exact around the exact model that you're using become a lot thornier, and you have to think about those.
Thank you. Let's thank Daniel again for a great talk.